the third video for class 12, and I want to do an example after we bring up a relevant application of reliability to our design factor. Now, if you can imagine, we have some variability in the stress, and we have some variability in the material strength. So there, the strength, we know average strength should be higher than the average stress, right? And that's usually what we're really calculating when we do design factor or when we're using a safety factor. But there's variability in both of those, right? There's some uncertainty, and so maybe we have enough data. We don't always have enough data, so sometimes that's why we use a bigger design factor. But let's say that we're able to run lots of tests, and we're able to measure or calculate the stress, and we're able to, from the batches upon batches of samples for strength, we're able to find what those are. Well, if you overlay them, this little intersection right here, that's going to be the population that's going to fail, right? That overlay right there. So we can use this coefficients of variance, which is just the standard deviation divided by the average. So you see you have capital CS and you have capital C sigma, and we could put them into this equation, and we find a design factor. A design factor to account and try to reduce the fact that we're going to have this right here. So by having a margin greater than that, we're then going to be able to be safer. And by how much safer? Well, we could figure out with a z. We could find a z, which is the normalized standard deviation. We could work backwards, and we could find out what the reliability is going to be. All right, so we can quantify how reliable something is if we use this design factor. Right? We can even, and it doesn't have to be this design factor. It could be any design factor that we could stick into this if we know this information. Now, truth be told, we don't always know this information, but we can find it. We can figure it out if it really mattered to us, right? If we were the CEO of the company and we wanted to really know, we'd run test after test. We'd spend the money to do the research to find out the variability, and we would use this as our means to determine. All right, so let's go to this example 1.6, which I thought was a pretty good one to use right here. So a lot of information. Let's keep track of it. We have cold drawn 1018 steel rod. All right, so so its yield strength, average yield strength is 78.4. Just as out of curiosity, we know that that's 1018 steel, right? And cold drawn, so we could look that up in table A20 in the book. That's 1018 cold drawn, and they're saying it's 78. And why'd they do that to us? I don't know. 1018 cold drawn. Well, yeah, not even close. That's weird. This says it's 54. Why would they do that? Oh, Joe. Joe Shigley? Why'd you let me down, Joe? Okay. So anyway, let's just use these values. All right. So magically, this particular batch has got a whole lot. So when it comes to strength, it's average. It's mu s, as we're going to try to use variables about the statistics, is 28.4. And its standard deviation due to strength is going to be 5.90 KSI. And the rod is subjected to a mean static axial load of 50 kips, right? So here's your average load here is 50,000 pounds, right? I don't like kips. And the standard deviation of this in terms of force, I'll use sub P right there. Nope, did wrong. My bad. Let's go with sigma, which is, this is going to be so confusing. It's going to be 4,100 pounds, right? So assuming the strength, right? So I'm going to replace this guy right here. That's what I should have done. P, right there, right? So here's the average, and here is the standard deviation. Assuming the strength and load have normal distributions, what value design factor corresponds to a reliability of 0.999 against yielding, or 99.9%, and determine the corresponding diameter of the rod that you should have there. Okay, so we're going to take first, we want a coefficient of variance, right? So we want a CP right here. Something that we're going to know, right? So I had to be like a little careful here. No, okay. So we're going to say that CP, right? Because we know that the stress, this is actually stress, not that, is going to be P over A, right? If they're the ones that decided that P was going to be the load, right? So with this is axial. Thing, they say that somewhere in there, right? That we're subjected to static axial load right there. So this is the stress. So we actually know that, this coefficient of variance that we need right there, it's going to be there. It's going to be the same area, right? So that's going to those two have to equal each other. So we'll take this sigma P and divide it by mu P, or 4,100 divided by 50,000. And we end up with 0.08200. And then we could do the same thing for the S right here, for the strength of the thing. So we take the standard deviation and divide it by the mean. So we have 5.90 and divide it by 78.4. And what we're left with is 0.07526. So now, what we can do with this, okay, so what I need in terms of these equations right here, let's take a look at this. You can find, right, so we need to have Z. We need the Z for this. We need the Z that corresponds with 0.999, right? So what I did, because this table is not easy to use and to look up, but I'm sure actually, well, let's actually, this maybe is a good time to interject introduce using Excel onto this right here. But in this table right here, if we had to use this table, that would be down here at the very bottom. So the next page, right, it continues on to the next page, and you would see that we have 0.999, right? That corresponds to a Z of negative 3.090, right? So that's the number of standard deviations, right? So it's like, we're talking about pretty far over to the edge of the thing, knowing that 3 standard deviations, right? We saw that 6 sigma thing, right? I described right there. There's 1 sigma, and right. So right there, so we had 1, 2, 3. If we're greater than 3 over here, or we're greater than negative 3, or we're if we're less than negative 3 here, or greater than positive 3 right here, we know, oops, I'm sorry, my hand was in there, that we're going to be like pretty far over there. So we're going backwards with our 0.99. So we say the Z of 0.999 is equal to negative 3.090, right? So if we need to do that, the Excel function that we would use for this is going to be, let's say we go 0.999, and we want to find what that is. So it equals, and we write that it's norm dot S Like we need to talk about the difference between the S and the P, right? Did they even show a P? No, they just go norm distribution. So you have returns the normal distribution for the specified mean and standard deviation. Ooh, and then we have okay, here we go. It gives you the inverse of the standard deviation here. All right. So we're going to go S dot INV, and then we put the reliability inside it. And you see what we get. We get 3.09 there. So it wasn't the negative. That's interesting. It wasn't the negative one up here. I see. Okay, another one we could do. We could go. Interesting. Let's see if we go backwards. Here's what we would do. Like if we wanted now to get the z from this, we'll go norm dot s dot dist, and we get of that. And now we need to type in true, right? And that'll give us go backwards, right? So if you want to get the z, if you know the r, the reliability, you get this. If you want to get the reliability and you know the z, you go to this, right? So you can see that the difference between there. There's the INV and there's the DIST. So that'll be kind of useful to us. But anyway, we got this thing right here, and now we need to populate the equation that they gave us for the 1 plus or minus the square root of 1 minus z squared, that guy squared, so it didn't matter whether it was positive or negative. The cs squared times 1 minus z squared c sigma, right there, right? And then all of that divided by 1 minus z squared cs squared. Be interesting to like mess with this and see how they got to this. I bet it's not that complicated to figure out, but I haven't messed with it any yet. So anyway, 1 plus or minus, and it'd be interesting to decide what the plus and the minus, what the differences are right in here. I think it depends on how big this thing is going to be. 1 minus, and then take the negative 3.090 and square it and multiply it by CS 0.07526 squared, another bracket, 1 minus negative 3.090 squared, and then so now it's going to be this guy, right? 0.8200 squared. Close that, and then divide by 1 minus z squared. Whoop, I need to write, I'm putting numbers in. 1 minus negative 3.090 squared, and CS is this guy, 0.07526 squared. And I found that I got 1 plus 0.3388, the stuff inside the square root. That was some of the point of this. And this on the bottom denominator is 0.9459. And I end up with a design factor of 1.415. And you could ask, okay, well, what should I use the minus? Well, you could try it out and say 1 minus 0.3388, and then divide by 0.9459, and you get 0.7. That doesn't make any sense as a design factor. No, not at all. What if I took the inverse of it? Not kind of close. No, it's not the same. Just curious. Okay, so the design factor, our conclusion is that the design factor is 1.42. I'm going to go ahead and stick with this as being our answer to that first part. And so now if we had, okay, so for the stress that we're going to calculate here, that would be P over pi over 4d squared. And that's going to equal to the yield strength divided by, and it's going to be the average yield strength divided by the design factor. So we could find as an equation, we get 4 times P design factor divided by pi sy right there, right? So we could find this, and we're going to use the average P here. So the average P was 50,000. And the design factor 1.415 divided by pi, and then the yield strength, the average was 78.4. So 78,400, and I get a design 1.072 inches. And so once again, my diameter, I already did this in a previous video. We go to table A17 with our preferred sizes. And I'm just doing it because you might not have watched the other video. But in our table A17, we see we have, for fractions of inches, 1 and 1 1/4. If we went to decimals, we have between, it goes between 1 and 1.2. So we have a kind of a choice. I decided to go with 1 and 1/4 again. So 1 and 1/4 or inches, which is 1.25 inches, you know, whichever way. I prefer to write it that way. So there's the answer. You get the idea. Now I'm going to do, I'm not sure how many more examples I'm going to do. I'm kind of tired, and I'm not sure anyone's going to watch them. But that was like 16 minutes worth of video.